Welcome to part 3 on chapter 6, propositional logic. Let us begin with an example. Suppose that I have a formula phi that is the AND of two subformulas alpha 1 and alpha 2. And now I'm interested in the question, what is the Boolean function b of phi that corresponds to phi? Well, the Boolean function, when receives a argument v, which is a binary string, equals the evaluation of the truth value of phi with respect to the assignment tau of v. Tau of v, I remind you, is the truth assignment that is induced by the binary vector v. Now, how do we evaluate the value tau hat v of phi? Well, what we do is we take phi and we break it into alpha 1 and alpha 2. And then the evaluation procedure is recursive. So we apply the Boolean function b and, which is the function that corresponds to the AND logical connective. And we take this Boolean function, which is a binary Boolean function, and we apply it to two bits. The first bit is the evaluation of alpha 1, and the second bit is the evaluation of alpha 2. But what is the evaluation of alpha 1? It is the application of the Boolean function that corresponds to alpha 1 to the binary vector v, and the second bit is b alpha 2 of v. We conclude that b phi of v equals b and of b alpha 1 v, b alpha 2 v. And this is what we have here in the depiction. We have our inputs. The inputs are fed to b alpha 1 and b alpha 2. They do an evaluation of two bits. These two bits are fed to the AND function, and they give us the result. And this is exactly the equality that we have written over here. So b of phi just takes the inputs, feeds them to b of alpha 1, b of alpha 2, takes two bits, does the AND between them, and gets the result. And in fact, the same method gives us the following lemma. If we have a binary logical connective that is applied to two subformulas alpha 1 and alpha 2, then for every binary vector, the function b of phi applied to v simply equals the b of the logical connective applied to the two bits b of alpha 1 v and b of alpha 2 v. So if we have this formula, this is the function that would correspond. I should have here this circle. Yeah, this is the same circle as here. Very good. Let's continue. Now, we want to claim that two Boolean formulas, P and Q, are logically equivalent if and only if the formula P equivalence Q is a tautology. Recall that this is the equivalence connective. Good. So, P is logically equivalent to Q if and only if, for every truth assignment, the truth value of P equals the truth value of Q. Now, the Boolean function that corresponds to equivalence just checks for equality. Therefore, the first line holds if and only if B of the equivalence of the two bits, the evaluation of P and the evaluation of Q, gives us a 1. Now, this part, the evaluation of P, is just BP of V for every V. Because here we have for every tau, so here we have for every binary vector, because we had a bijection between binary vectors and truth assignments. So we can write here BP of V equals BQ of V. Or in other words, the Boolean function that corresponds to the equivalence connective outputs a 1 when assigned the two bits BP of V and BQ of V. Now, this, by the lemma that we just showed, means that B of P, if and only if Q, or equivalence Q, of V equals 1, because this is exactly what we just showed. This is this claim where the circle connective is the equivalence connective. Good. And this means, if this holds for every binary string, this means that P equivalent Q is a tautology. And that completes the proof. One thing we like to do is to substitute subformulas in formulas. Let me show you an example before I describe this thing. I have here formula phi, which is x1 or x2. I have a formula alpha 1, which is x and 0. And I have a formula alpha 2, which is not of y. Now what I want to do is I want to substitute. I want to replace x1 with alpha 1 and x2 with alpha 2. So what I get is a parse tree that begins like the parse tree of phi, and every time I see an x1, I replace it with the parse tree of alpha 1. Every time I see an x2, I replace it with a parse tree of alpha 2. And now I get a new formula denoted by phi of alpha 1, alpha 2. Okay? So let's go back to our example. Our goal is to compose large formulas from small ones. We deal with, for simplicity, with formulas over two variables, x1 and x2. You could generalize it to any number of variables. So we have formula phi, which is a Boolean formula over the variables x1 and x2 and uses a set of connectives C. And we have two formulas, alpha 1 and alpha 2, over an arbitrary set of variables and the same set of connectives. Now, we take the parse tree of phi and we apply substitution. What does substitution imply? Every time in the parse tree we see xi, we replace this leaf marked by xi with a new copy of the parse tree of alpha I, as we did in the example. Okay, we saw x1, we replaced it with alpha 1 to get it here. We saw x2, we replaced it with alpha 2, and we got it here. This is substitution. And we denote the formula that is obtained by this substitution by phi in parentheses alpha 1, alpha 2. Alpha 1 and alpha 2 are not the variables of phi. They are subformulas that are substituted for the occurrences of the variables inside phi. Now, this substitution can be viewed as a simple find and replace procedure. So I have this formula. It has the variables x1 and x2. And every occurrence of x1 is replaced with the formula alpha 1. So you see I did it twice. And every occurrence of x2 is replaced with an instance of alpha 2. And now I get phi of alpha 1, alpha 2, which is a bigger formula, because here these are leaves, and here alpha 1 and alpha 2 can be arbitrarily large parse trees. Now, this idea of substitution can be easily generalized to formulas over k variables for any number of variables. And then phi of alpha 1 up to alpha k is obtained by replacing every instance of xi by alpha I. Okay, so the first lemma that I want to prove that uses substitution is that for every truth assignment tau, the truth value of phi of alpha 1, alpha 2 equals the application of the binary function that corresponds to phi. Recall that phi is just a Boolean formula over two variables, where I input here 2 bits, the evaluation of alpha 1 and the evaluation of alpha 2. So here's a depiction of what the lemma states. I have here phi, which is over two variables, x1 and x2. It is the AND of the OR of x1 and x2. And here I have the XOR. This should have been a XOR to make it more interesting. Let's see if I can... It's not important. You could have two ORs. It just looks silly because the formula then is not very interesting, because it's the AND of the OR and the OR of the same thing. So let's make it here XOR. And let's make this XOR. Very good. So now we have the formula phi of x1, x2. This is an OR, this is XOR, this is x1, x2, x1, x2. Now we replaced x1 by alpha 1, x2 by alpha 2, and so on. Now, let's assume that tau assigns the value 0 to x1 and 1 to x2. Okay? So when I do the evaluation, I will have here OR of 0 and 1, this will be a 1. In here I'll have a XOR of 0 and 1, this will be a 1. And then I do an AND, and I get a 1. Okay? Good. Now let's look at the formula phi of alpha 1, alpha 2. And I want to evaluate the value of this formula, right? So what do? I recursively evaluate alpha 1 and alpha 2, and let's say that the truth value of alpha 1 is 0, and the truth value of alpha 2 is 1, right? So I have here this 0, 1, 0, 1 pattern along the edges that I have here in this case. So now from this point on, the evaluation is the same, which means that the evaluation will be the application of the Boolean function that corresponds to phi on the 2 bits, on the 0 of the x1 and the 1 of the x2. But here, it is not x1 and x2 which are actually the arguments. It is the evaluations of alpha 1 and alpha 2. So this is what the lemma says. Let's prove this lemma. And the main reason that I want to prove this lemma in a precise fashion is because I will introduce a new type of induction, okay, that you haven't seen so far. So what I will do, I will prove it by complete induction, but complete induction over what? I will prove it by complete induction over the number of vertices in the parse tree of phi. Okay, so recall, I have originally a formula phi, and this formula, I can count the number of vertices in the parse tree. So in this formula, the number of vertices is 1, 2, 3, 4, 5, 6, 7. So I have 7 vertices in the parse tree of phi, and I'm doing the induction on the number of vertices in the parse tree of phi before the substitution. Good. The base case is when the number of vertices, I just want to mention that counting the number of vertices in a parse tree is a very common thing, and very often it would be called the size of the formula or the size of the parse tree of the formula. So when we talk about the size of the formula, it is not the number of variables in the formula, but the number of vertices in the parse tree of the formula. Very good. So let's start with the induction basis when the number of vertices is 1. If the number of vertices is 1, then what can we say about phi? What are the possibilities for phi? Okay, so we say phi could be a constant, could be 0, could be 1, or it could be a variable. Now we only have 2 possible variables because we have assumed that phi is over 2 variables, x1 and x2. So the first possibility is that phi is x1, and the second possibility is that phi is x2. These are the 2 possibilities. Now I will focus on 2 possibilities, and I'll leave the other 2 as exercises. So we will address the case that phi is 0 and the case that phi is x1. The other cases, I'll leave them as exercises. Okay, let's assume that phi is 0, and we want to prove that the left-hand side equals the right-hand side. Okay, so if phi is 0, what happens when I substitute x1 with alpha 1 and x2 with alpha 2? Well, x1 and x2 do not appear in phi. So after substitution, phi remains 0. This is an important observation. What is the Boolean function that corresponds to a formula which is 0? It is the constant function which always gets the value 0. So what can we determine? We can determine that the right-hand side is the value of the constant function 0. So the right-hand side is 0. What can we say about the left-hand side? Well, the left-hand side is the evaluation over this phi of alpha 1, alpha 2. But phi of alpha 1, alpha 2 is 0. So it's the evaluation of 0. The evaluation of 0 is 0. So we get that the left-hand side equals the right-hand side, and the induction basis holds for phi that equals 0. Try to prove it for phi equals 1. Now, let's consider the case that phi equals x1. We're still in the induction basis. Okay, well, if phi equals x1, what happens when you substitute x1 with alpha 1 and x2 with alpha 2? You will get the formula alpha 1. And what is the binary function that corresponds to phi? Phi is nothing but x1. So it just looks at the value of the first variable, right? So if you get 2 bits, an assignment for x1 and an assignment for a truth value for x1 and a truth value for x2, then it will output the truth value of x1, namely b1. Okay, so what can we say about the left-hand side? The left-hand side, tau hat of phi of alpha 1, alpha 2. Well, phi of alpha 1, alpha 2 is just alpha 1. So we will get tau hat of alpha 1. What can we say about the right-hand side? What's written over here? Well, this fellow is just the first coordinate, because b phi of 2 bits is the first bit. So we get here 2 bits, and we output the first bit. So we get that the left-hand side equals the right-hand side, and that completes the induction basis for the case that phi equals x1. I leave it as an exercise to prove the induction basis for the case that phi equals x2. As you can imagine, it's a very similar proof. Okay, so we have the induction hypothesis. It tells us that for every formula, if the formula size is at most n, then the claim holds. Now in the induction step, we want to consider a larger formula, a formula where the number of vertices is n plus 1. And we need to consider 2 cases. In the first case, phi is the knot of phi 1. I'll leave this case as an exercise. And in the second case, phi is phi 1, some binary connective, phi 2. And you can think of this binary connective as or and whatnot. Okay? Very good. Okay, so suppose that phi is phi 1, some binary connective, phi 2. What does the induction hypothesis tell us? The induction hypothesis tells us that if we take phi 1 or phi 2, I denote it by phi I, and substitute x1 for alpha 1, alpha 1 for x1, alpha 2 for x2, and evaluate its truth value, this will equal the application of the binary function that corresponds to phi I with respect to 2 bits, the evaluation of alpha 1 and the evaluation of alpha 2. Okay, that's the induction hypothesis. When applied to the 2 subformulas, phi 1 and phi 2. Notice we needed here complete induction because the size of phi 1 and the size of phi 2 is not n, it is less than n. Okay, good. Now we take the left-hand side and we ask ourselves, how do we evaluate the value of the function of the truth value of the Boolean formula phi? Well, it equals b of the binary connective applied to the truth value of the left side and the right side. What is the right side? Sorry, the left side. It's phi 1, where you substitute each occurrence of x1 by alpha 1 and each occurrence of x2 by alpha 2. And similarly, the right-hand side will be the evaluation of phi 2 with respect to the substitutions alpha 1 for x1, alpha 2 for x2. Okay. Now we can apply the induction hypothesis. What does the induction hypothesis tell us? It tells us that this part equals this part, and that this part equals this part. This is the application of the induction hypothesis. Good. Now what we do is we apply the claim that we just saw. Please remember, we had a claim. This was a claim that we have. Where is the claim? Here it is. If we have phi, which is some binary connective of 2 subformulas, and you want to know what its value, well, you can decompose it. So now we're going from this direction to that direction. Very good. So now we get this thing. So B star of B of phi 1, B phi 2 is B phi 1 star phi 2 with respect to the two bits that we have over here, tau hat of alpha 1 and tau hat of alpha 2, and that completes the proof. Now, let's consider the following situation. I have a formula phi, I have a formula alpha 1 and alpha 2. Phi is over two variables, alpha 1 and alpha 2 are over any number of variables. Now, I take a formula phi hat, which is logically equivalent to phi. You can check that these two formulas are logically equivalent. This is in fact De Morgan's law. We will get to that later. Alpha 1 is logically equivalent to alpha 1 tilde. You can check this also by checking all the four cases. And alpha 2 is logically equivalent to alpha 2 tilde. Now, I take phi and I substitute every occurrence of x1 with alpha 1, every occurrence of x2 by alpha 2. So I get this formula, and this is the expansion of what I get after I do the substitution. And I do the same thing with phi tilde, alpha 1 tilde, and alpha 2 tilde. And I get this formula. Okay, so phi is logically equivalent to phi tilde. Alpha 1 is logically equivalent to alpha tilde, alpha 1 tilde. Alpha 2 is logically equivalent to alpha 2 tilde. And now I get these two formulas, phi of alpha 1, alpha 2, and phi tilde of alpha 1 tilde, alpha 2 tilde. What can I say about these two formulas? Well, in fact, they are logically equivalent. Okay, so I start off with the formula phi over two variables, phi tilde over the same two variables, but possibly with a different set of connectives. I have two formulas, alpha 1 and alpha 2, over arbitrary variables, the same connectives as phi, and the tildes here with the same connectives as phi tilde. And alpha 1 is logically equivalent to alpha 1 tilde. Alpha 2 is logically equivalent to alpha 2 tilde. Phi is logically equivalent to phi tilde. Then phi of alpha 1, alpha 2 is logically equivalent to phi tilde of alpha 1 tilde, alpha 2 tilde. Let's see an example. Okay? So I start with the formula I start with the formula beta, which is x and y or z. Okay? Now, the problem that I have here with this formula is that the set of connectives that I want to use is and in XOR. I do not have OR in C. So I want to somehow find a new formula, beta tilde, such that beta tilde is logically equivalent to beta, and it uses connectives and in XOR. It does not use the OR. Okay? This is my goal. So what do? I view beta as the substitution of alpha 1 and alpha 2 into phi. So my phi is x1 or x2. This is the root here. You see the root is OR, and this will be x1 or x2. And I substitute. For x1, I substitute x and y. So my alpha 1 would be x and y. My alpha 2 is simply z. And in fact, I have in C, I have the AND and XOR connectives. So I can write alpha 1 tilde, which simply equals alpha 1, and alpha 2 tilde, which simply equals alpha 2. And my goal is to find phi tilde, which is logically equivalent to phi, using only the connectives AND and XOR. These are the two connectives that I do have. Okay. Luckily, I can find this formula, phi tilde, which is x1 XOR x2 XOR x1 and x2. And you can verify that this formula, phi tilde, is logically equivalent to the formula phi, which is x1 or x2. Okay, now I can substitute. I can define beta tilde to be phi tilde of alpha 1 tilde, alpha 2, or alpha 1, alpha 2, because they are the same. There's no difference. I do the substitution, so x1 is substituted with alpha 1, x2 is substituted with alpha 2, x1 is substituted with alpha 1, x2 is substituted with alpha 2. Great. Now, what is alpha 1? Alpha 1 is x and y. Here it is. What is alpha 2? Alpha 2 is z. So I just plug in z. And I get this, I continue in this fashion, and I get this new formula, beta tilde, which, by the claim that I haven't proven yet, by this corollary, is logically equivalent to beta. And I got rid of the OR connective, and I'm using only the connectives and in XOR in beta tilde. You see, I have in AND, XOR, XOR, and AND. Okay, so let's prove the corollary. So, from this point on, instead of writing phi is logically equivalent to phi tilde, I'll write this double-sided arrow with 2 lines rather than 1 to distinguish it from the equivalence connective. So phi is logically equivalent to phi tilde, alpha I is logically equivalent to alpha I tilde, implies that this holds. Okay. Good. So in order to prove that this is logically equivalent to that, it suffices to prove that for every binary vector that actually determines an assignment to all the variables, the extension of this assignment to phi of alpha 1, alpha 2 equals the evaluation with respect to the same assignment to phi tilde of alpha 1 tilde, alpha 2 tilde. Okay, so let's prove this. We take the left-hand side, and we notice, what is this thing? This is the application of the function that corresponds to phi with respect to the 2 bits, the evaluation of alpha 1 and alpha 2. This is an application of the claim we just proved. Now, we can replace phi with phi tilde, because these 2 functions are equal if phi and phi tilde are logically equivalent. This is something that we also proved. And the same holds with alpha 1 and alpha 1 tilde and alpha 2 tilde with respect to the evaluations. This is a thing that we also proved about logically equivalent Boolean formulas. And this thing, by applying the same lemma that we used here, gives us this part, and that completes the proof. Okay. Now, what we saw is that every Boolean formula P, every Boolean formula P, if P is a formula, can be interpreted as a Boolean function B of P, which is a Boolean function. Okay. So now we want to ask ourselves the following question. Which sets of connectives enable us to express every Boolean function? So we say, a Boolean function B is expressible by Boolean formulas over n variables and the set of connectives C. Notice that the n here is the same n over here. This is the number of bits in the domain of B. So we say that this function is expressible by this set of connectives if there exists a formula P such that B equals B of P. And then a set of connectives is complete if for every Boolean function B, if every Boolean function B is expressible by a formula in this set. Namely, for every Boolean function, there exists a formula using these connectives such that B equals B of P. This is what we want to prove. This is our definition. Now, it is not clear up front that there exists any set of connectives that is complete. Might be the case that it's not complete, right? For example, you can think, you can think of real functions and think of the subset of real functions which are polynomials and ask yourself, does there always exist a polynomial that, is it true that for every real function there exists a polynomial that equals that real function? And the answer is obviously no. So the set of polynomials is not complete with respect to the set of real functions. But here we kind of hope that there exists a set of complete connectives such that every Boolean function is expressible by a Boolean formula. Okay, so let me prove that the set of connectives, not, and or, three connectives, is a complete set of connectives. Okay, how do you prove such a claim? I want to show that for every Boolean function there exists a formula that uses these connectives such that the function that corresponds to the formula equals our function. How do you prove it? We will prove it by induction. Induction on what? On the number of bits in the domain of the Boolean function. So you think of your favorite function b over n bits, and our goal is to find a Boolean formula that uses the connectives not, and, or, such that this formula induces a Boolean function that equals b. Okay, so let's start with the case, the induction basis, which is n equals 1. What does it mean when n equals 1? How many functions do you have from 1 bit to 1 bit? You should enumerate all of them and show that for each such function, you can express it by a Boolean formula that uses or, and, not. So I'll leave this as an exercise. Let's focus on the induction step. So now I have a function over n bits, and I assume that every function over n minus 1 bits is expressible by a Boolean function, by a Boolean formula over these connectives. Good. Now let me define two functions, g and h. Both of them are functions with a smaller domain. So both g and h are functions from 0, 1 to the n minus 1 to 0, 1. Therefore, I can apply the induction hypothesis to both g and h. How are g and h defined? Well, the way that g is defined is you compute the value of b with respect to the same set of bits, but you're missing one argument. So the last argument is always set to 0. And how is h defined? Again, using b with the same arguments, you're missing one argument, so you always pad, in the last argument, vn, you pad a 1. Okay? So g and h are defined using b by restricting the last argument, the last bit, to be 0 and 1 respectively. Okay. So now I want to apply the induction hypothesis to g and h. So what does the induction hypothesis tell me? It tells me that I have formulas r and q using these connectives, c, which are not, and or. I can use these connectives in order to express both h and both g. So the Boolean function that is induced by r equals h, and the Boolean function that is induced by q equals g. Okay, so now what I do is I build this very nice formula, p, which is defined to be qn not xn, or r and xn. And I claim that the binary function that corresponds to p equals b, the function I started with. Okay, how do I prove this? Let's look at this depiction of the formula p. So p is the or of two ands. The left and is the and of q and xn bar. The right and is the and of r and xn. Now, recall, the induction hypothesis tells me that q expresses the function g, and r expresses the function h. Okay, so now you give me b over n bits. You ask me to evaluate b over some n bits. The last bit is either a 0 or a 1. Suppose the last bit is a 0. If the last bit is a 0, then over here I have a 0. This will be a 0. And an AND with one input, which is a 0, will give me a 0. Now, xn is a 0, so I'm assuming here xn is 0. Xn is a 0, so not xn is a 1. What can I say here? This is g. What can I say over here? This is g of v1 up to vn minus 1, and the last bit is a 0, right? So I get here b, so this part will be b of v1 up to vn minus 1 comma 0. And the 1 with the and will give me the same bit. So I'll get the same bit over here. And now I'm doing this OR, so I will get here b of v1 up to vn minus 1 with a 0. And this is exactly what I needed to compute. Okay? And you can do the same type of verification for the case that the last bit is a 1 in b. Very good. Therefore, the formula P indeed expresses B, and that completes the proof. You will see in the recitation a second proof of this theorem. This is a very important theorem. You will see a second proof of this theorem that tells us that this set of connectives is indeed complete. Now, suppose I give you a set of connectives C tilde, and I tell you that with C tilde, I can express the Boolean functions that correspond to not, and or. What can I say then about C tilde? I claim that under this assumption, C tilde by itself is a complete set of connectives. This means that if you want to prove that C tilde is a complete set of connectives, you don't need to be able to express all the possible Boolean functions. It suffices to express 3 Boolean functions, not, and or, which by themselves form a complete set of connectives, and that will imply that C tilde is also a complete set of connectives. Let me provide you with a proof. Okay, so we want to prove that if you can express all these 3 Boolean functions using connectives in C tilde, then C tilde by itself is a complete set of connectives. Good. You need to prove that for any function b, there exists a formula beta that uses sorry, this is a mistake. What I should say here is that the completeness of not, or, and tells me that for any function b, there exists a formula that uses these connectives such that b equals b of p. Now my goal is to find a beta tilde that is logically equivalent to beta, and therefore b of beta tilde will actually equal b of beta, which equals b, and that will complete the proof. Now this beta tilde is supposed to be a formula that uses the connectives in C tilde. Okay, so this is my goal. I have reduced the problem of proving the theorem to the problem of given a formula beta over the connectives not, or, and, find a logically equivalent formula beta tilde over the connectives in C tilde. How do I do this? By complete induction on the size, I denote the size of the parse tree by n, of beta. So I'm counting the number of vertices in the parse tree of beta, and I'm applying complete induction. Okay, the base case, when n equals 1, I'm leaving it as an exercise. Recall that in this case, what can beta be? Beta can be either 0, 1, or a variable, right? Some xi. So you need to prove this case. It's a very easy case. Okay, the induction hypothesis is that the theorem holds if the size of the formula beta, size of beta, is less than or equal to n. Okay, so now I need to prove the induction step. Now, beta is a formula that uses connectives not, or, and. So the root of beta is marked by an and, by an or by a not. So I will prove the case that the root is marked by an and I'll leave it as an exercise to prove the cases that the root is marked by a not, or by an or. Okay. So here's my beta, and I'm looking for a beta tilde over the set of connectives C tilde that is logically equivalent to beta. Okay. Now alpha 1 and alpha 2 are strictly smaller than beta, so I can apply the induction hypothesis to alpha 1 and alpha 2. So let alpha I tilde denote Boolean formulas over C tilde such that alpha I is logically equivalent to alpha I tilde. Again, this is simply the induction hypothesis. Now, let phi of n denote a Boolean formula over x1 and x2, in fact, because it has only two variables over x1 and x2, such that x1 and x2 is logically equivalent to phi of n. And how do I know that there exists such a formula? Because I told you that there exists a formula over C tilde that expresses B and. So there exists a formula that is logically equivalent to x1 and x2. Okay, so now my beta is alpha 1 and alpha 2. The and is logically equivalent to phi of and. Alpha 1 is logically equivalent to alpha 1 tilde. Alpha 2 is logically equivalent to alpha 2 tilde. Therefore, I know that beta is logically equivalent to this formula. And this formula only uses the connectives in C tilde. And that completes the proof. Okay. Tautologies. Recall, tautology is a formula, Boolean formula, that always evaluates to the truth value 1 regardless of the truth assignment that you give it. So tautology, so we say that phi is a tautology means that for every tau hat of phi is 1, where tau is a truth assignment. Okay, so now I claim that all these formula are tautologies. And they actually are so famous that they have names. X or not X is called the law of the excluded middle. Double negation. X is equivalent to not X. Modus ponens. If X implies Y and X, then Y, sorry. So if you want to prove Y, you need to prove X, and you need to prove that X implies Y. Contrapositive, we saw this before. X implies Y is equivalent to not Y implies not X. Material implication. X implies Y is equivalent to not X or Y. And the law of distribution, X and Y or Z is logically equivalent to X and Y or X and Z. Now, how can we verify that all these are indeed tautologies? Well, all these formula are over 2 or 1 or 3 variables. So all you need to do is check all the possible truth assignments and verify that regardless of the truth assignment, the truth value is 1. Now, suppose that so let me first recall the lemma that we showed before, that if I have phi and I substitute x1 with alpha 1 and x2 with alpha 2, then the truth value of phi with these replacements is the application of the Boolean function that corresponds to phi with respect to these 2 bits, which are the evaluations of alpha 1 and alpha 2. And recall, think of phi as a small formula and alpha 1 and alpha 2 as very big formulas, just for the sake of the question I'm about to ask. Okay, so I'm thinking of alpha 1 and alpha 2, which are any Boolean formulas, perhaps, with millions and millions and millions of variables and I don't know how many vertices. Now I take the formula phi, which is alpha 1 or not alpha 2, alpha 1. What can I say? Is phi a tautology? I know that X or not X is a tautology. But here I have let's write x1. But here I have substituted x1 with alpha 1. So I have the formula alpha 1 or not alpha 1. Is it a tautology? Well, we have a theorem or a lemma. The lemma tells us that the truth value, after you've done the substitution, is the application of the Boolean function that corresponds to phi with respect to these 2 bits. Now, if phi is a tautology, what do we know about this function, b of phi? So if phi is a tautology, we know that b of phi is a constant function 1, always attains the value 1. Therefore, this means that this formula is a tautology. Okay? Very good. Let's consider the following formula, this one. Well, this one has the form of a tautology that we just saw, right? Sorry. Alpha 1 implies alpha 2 is if and only if not alpha 1 or alpha 2. This is not contrapositive, sorry. This is a material implication, okay? But here, instead of x and y, we have subformulas, alpha 1 and alpha 2. Again, by applying the same lemma, we get that this formula is a tautology. Okay. Now I want to talk about two tautologies, which are, in fact, De Morgan's laws, when applied, when viewed in propositional logic, not identities over sets. And these two tautologies are, again, very easy to prove. You just check all 4 possible truth assignments. Now, I want to prove De Morgan's law for sets. This is an old debt that I have from the first lesson. I want to prove that for any 2 sets, the complement of A union B equals the complement of A intersection the complement of B. And surprisingly enough, the proof is not that short, but not complicated. So let's see. I need to prove that X is in the left-hand side if and only if X is in the right-hand side. Okay? That's what I need to prove. Good. So X is in the complement of A union B if and only if X is not in A union B. In other words, it is not true that X is in the union of A and B. Okay, so what does it mean that X is in the union of A or B? It means X is in A or X is in B. Okay, now we want to harness propositional logic. So let Y denote X is in A. Let Z denote X is in B. So what we have in this line is not Y or Z. Good. Now, we know that not Y or Z is logically equivalent to not Y and not Z. This is exactly De Morgan's law. Good. Now, let's see. Not Y is not of X in A. Not Z is not of X in B. We're going back to sets. Not X in A means X is in the complement of A. Not X in B means X is in the complement of B. And we have an and here. So this means that X is both in the complement of A and in the complement of B. And that completes the proof because we get that an element is in the left-hand side if and only if it's in the right-hand side. Thank you very much.